Yes, exactly. So actually, that's one of the good like discussion points. So for this particular case, actually we've tested that if you train on like just one or two diseases, it will perform much better than like 14 diseases. Yeah, in this case, because you can think it's sort of more focused, so it can like get much better. But for some other use cases, there's probably no very obvious evidence there. So that's, I think it's case by case. Yeah, but no harm to try, of course. Yeah, the number of models, and like sometimes it's like a trade-off between the final production, because you don't need to, for example, if you really want to predict like 4 diseases, you don't want to probably go through 4 models in sometimes. Yeah, so like a trade-off thing. Okay, question. You mean like why do we choose DenseNet? Yeah, so actually we tried a couple of different neural network architectures, and DenseNet performs the best. So yeah, that's one of the particular reason. But I think there are also like, because if we just frame this problem as a data science problem, then there are like tons of different architectures you can choose. So you can of course choose some other advancements in this field, of course. Yeah, and sometimes they are likely to have better performance on this particular data set. So so if you really want to start very like easily, then if you go to Keras website, then there are like different architectures that you can choose. For example, we choose this one, the DenseNet, but you can also choose this one called Inception, ResNet v2, or etc. etc. So they are, I would say, all of them are a bit old. Like even the latest one, it was like developed like 2 years ago. So if you can also read a few other research papers. There's one very recent paper called DPN, dual path neural network, where achieves like one of the state of art like result in ImageNet, and I believe that will also apply to this chest X-ray dataset. Yeah. Uh huh. Uh. Uh huh. Uh huh. Yeah. Below. Like how do you get the cam the pictures? Uh huh. Uh huh. Oh, I see. I see. Okay. So yeah, that's a great question. That's a great question. So, um, in that okay, since people are interested in that, then let's dig a little bit deep into this cam thing, this visualization thing. So the key point there is that um, in order to so okay, so we talked about a lot of great stuff of this cam thing, class expectation mapping, but actually there's one huge uh, limitation of this neural net of this algorithm, which is it needs to have this layer called GAP, which stands for a global average pooling layer. So basically, the key idea is that it needs to have this global average pooling layer in order to apply this algorithm. And in order to get those global average pooling layer, we kind of uh, like, because for the final classifier, you can think there are a lot of convolutional layers here, and we have this global average pooling layer, and then we have the final classifier. So in order to get this global average pooling layer, get the value here, we want to chop off all the layers after the global average pooling layer. That's why we chop off the final 3 layers. Yeah. Yeah, we chop it off. So so we actually do 2 things. So for the final score, which is like no matter it's the ROC score we just see, or it's the single digit number we reported. So they are all come through the final classification layer, which it will give you a number, right? But for this visualization thing, we don't need the final 3 layers. We just need the layer till here. So that's why we also chop the final 3 layers. No, we didn't freeze any layers there. Yeah. So we initialized the whole layer with the model weights trained on ImageNet as the good start, but we didn't freeze any layer at all. So basically, because this dataset is huge enough, so we can train the model from end to end. But in other cases, like you just have like 20 pictures or like 100 pictures. In that case, you definitely want to freeze a lot of layers. Okay, any other questions? Okay, so hopefully because this tutorial, because I kind of tested everything, so hopefully you can run through this tutorial or this Jupyter Notebook without trouble. But if you do, just let us know. Okay, then let's go to the second part. So the second part will be focusing on how you actually train the model, because very likely you don't need to use our pre-trained model because you have your own dataset, you have your own problem. So this describes how you can train the model from scratch for this particular problem. So if you go to the second tutorial, Jupyter Notebook, we'll have this one here. So first we'll import a lot of okay. So we import a lot of stuff, and we define a few of the variables. We already gone through the image classification introduction part. So basically, that's why we frame this as an image classification problem. And for any image classification problem, one of the big tip is that you definitely want to visualize the data before you actually do any training. So in this case, let's go to some of the data. So let's say we want to visualize another image like this. So okay, looks good. This is like the input image. And then we want to see what are the labels. So in this case, we will read the label. It's this line where we are using pandas and use pandas to read the label file, and then we print the label file. So the labels is like this, where you have this image index, which stands for the file name of the particular image, and we have this finding labels. So please know that this labels is mined by NLP algorithm rather than labeled by the actual radiologist. And we have this follow-up number, which indicates that whether the doctors want to follow up with a particular patient. And we have this patient ID, which is corresponding to the number here. So for example, we have the patient ID 2 here, then the image index, we have number 2 here. And the gender of the patient and the view of the view position. So basically, there are 2 views in this particular case. We have PA view and AP view. So basically, one of them is like the X-ray is like you are facing the X-ray machine, and the other position is that you are like your back is facing the X-ray image machine. But in reality, actually, radiologists always need some other views, like the lateral views. But in this particular case, we just use the PA view or AP view. And we have the image, some information about the image, like we have the weight, the height, etc., etc. So yeah, we also, because the image here is actually in JPEG format, but in the reality settings, it's usually in some medical format called DCOM. So in that case, this is actually exported from the DCOM format. That's why they also have this kind of data saying, okay, what's the ratio of the exported image versus the original image. Okay, so we took a look at the label, and we see that the label is actually very interesting. For example, for a particular patient, for the patient number 3, so he has hernia like for almost all his chest X-ray images, which also makes sense. So we also observe that there are no finding labels, meaning that the patient is healthy. And we probably see that there are a lot of no finding labels, indicating that probably the data set is very biased, where you have a lot of healthy patients and you have just a little bit of a patient that have what kind of disease like infiltration or pneumonia, etc., which also makes sense. So after observing the labels, let's split the data into train, validation, and test dataset. So in this particular case, because we just have 100 patients, so for the first thing we want to make sure that we don't want the patient we don't want all the images. So we want all the images of a particular patient to stay either in the training set or in the validation dataset or in the test dataset. Because otherwise, for example, if we split by the image number, then it will be likely that, for example, the patient number 3, the first image is in the training dataset, the second image is in the validation dataset, etc. That will, of course, boost our score, but that's not what we want, because that will cause data leak problem. So in this particular case, we're actually dividing the validation, training, test dataset based on the patient number, so that we are sure that the images of a particular patient falls into a certain training set or test set. So in that case, we are dividing the different data set by the patient ID, like here. And we also read the labels from the original CSV file. And if we run this label, it will have 70 patients in the training set, 10 patients in the validation data set, and 20 patients in the final test set. So this data set here is just like 1% of the original data set. So in the original data set, you will have much more patients than here. So this is just for demo purpose. And then let's run through this cell. In this cell, we define a few of the important hyperparameters. One of the most important hyperparameter is called a learning rate. So in this case, we need to like tune this a lot during the actual training part. But in this case, we already tuned, and we select this one as the best learning rate. And we also define a few of the other parameters. So one thing in particular is that we want to resize the image, because the original input image is like the resolution is still very high, but we want to lower the resolution so that it can go through the training process. For example, here we are choosing 224 by 224, which is like a canonical number in image classification tasks. And if you want higher resolution, let's say you want like 500 by 500 or like even 1000 by 1000, you will likely meet other problems. For example, your GPU might be out of memory, etc. So you also want to tune this number a little bit. So the number of channels, we put 3 here, but actually it should be just 1. And we have 3 here because we want to reuse the weights from the other dataset, which is the image dataset, the ImageNet dataset. So we put the number 3 here. But actually, for this particular image, it just have 1 channel, and this is grayscaled. And the epochs here, so we put 2 for demo purpose, but usually you want to like train at least 10 epochs to make sure that the model is converged. And batch size, it determines like what's your mini batch looks like. So in this case, we have 16, but depending on your actual setting, you can have like 32, etc. And we have this joint class called data sequence. Basically, the idea is that we don't want to, so in this particular case, we are using CPU to train our dataset, but in reality, you definitely want GPU to train your dataset. And to use GPU to train your dataset, you want to maximize your GPU because GPU is super expensive, and you want to maximize the ability of GPU. In that case, you want to do a lot of pre-processing in your CPU, like loading the data into memory, into CPU memory, and doing like a few of the pre-processing, like flipping the dataset a little bit, or doing some like zoom in, zoom out, etc., etc. Of course, you can do that with GPUs, but that will be very not cost efficient. So in that case, you want to do that in CPU. And what this class gen sequence do is that it will do all those kind of dirty work on CPUs so that your GPU can be fully utilized. So you have so we define this class here, and we already talked about the network architecture, which is DenseNet. Again, we need to build the model. So, and let's run the model. So the model is, so first, this is just some demo. So we just use 1% of the original data set, and we use CPU to train our algorithm. And in reality, you definitely need to use GPU. That's why it's actually very slow. It takes around 5 minutes to just train on 1% of the original data set. In reality, if you have a powerful enough GPU, so you can actually train the whole data set in just 5 minutes. So we also define a few of the other convenient functions. And in this particular case, we define the model checkpoint, where we want to checkpoint the model every epoch. And we also have a learning rate decay schedule. So people usually tweak this a lot, but basically the idea is that we don't use a constant learning rate. Instead, we use a decayed learning rate. For example, the learning rate will start with a large value so that the model can find some decent starting point, and then we kind of lower the learning rate so the model can fine tune. Usually the learning rate is like that, and then there are some smarter people, they say, why don't we use like a recurring learning rate, etc., etc. So there are a lot of innovations there in that space. But in this case, we just use a decayed learning rate. And we also have TensorBoard here so that we can visualize the model, we can visualize the training process, and etc., etc. And finally, we have this piece of code where we actually train the classifier. So we have different input here, and the input would be the data generation sequence we just defined, and there are also a few other parameters. And as you can see, I already started the training. And for each of the batch, it takes, I don't know, like around 1 minute for each of the training step. And the ETA for this particular epoch is around 6-7 minutes. And that's just for 1% of the training data set. So I'll stop here a little bit so that people can run through this piece of code. Yeah, this is run on CPU. On GPU, it should be around 100 times faster. They are like they are not in the same visit, basically, like subsequence kind of thing. Yeah. Yeah, probably. Yeah. So that's why there are actually a lot of things you can do with this particular dataset, because for this demo, we just frame it as a independent image classification problem where we just say, okay, we don't care whether you are whether all the images are belonging to a particular patient or not. We just say, okay, this is like that, like they are just individual images. But like those kind of follow-up numbers, those kind of the fact that some of the images belong to the same patient, the fact that the age of the patient and the gender of the patient, etc., and even probably the view position of the particular chest X-ray images, they are probably also very helpful there. Oh yeah, we actually do. So I think, yeah, I think it's in the code. It's okay. So it's not in this particular tutorial, but if you go to that particular GitHub repository, you will see the full training code. So we do actually a lot of data augmentation there, like flipping, especially the horizontal flipping, because you don't want to do like vertical flipping because that doesn't make sense. Yeah. And like zooming in, zooming out, changing the pixels a little bit. Okay, so let's go to the model evaluation part a little bit more. So let's assume you already trained the model using GPU, etc., etc. So, by the way, for this particular model, so we have two versions of the code. So we have a PyTorch version, and we also have a Keras version. So the Keras version is a little bit slow, and for the Keras version, it usually takes like up to 24 hours to train a good enough model. And for the PyTorch model, it's more performant, and we also did a lot of optimizations there. So for the PyTorch version, it can like train the whole model within like 4 hours. So that's also available in the GitHub repository. And let's say you already have the model, but the next step is that you want to know whether the model is good or bad, whether it can be used in production or not, right? So in that case, some people might ask, okay, why don't I use, let's say, accuracy as the final metrics? So the answer is definitely no, because you definitely don't want to do that, because for most of the medical images, the positive like rates, they are actually very low. For example, for this data set, pneumonia only accounts for like almost 1.3% of the whole data set. So we can just tweak the number, saying, okay, we just predict every patient to be pneumonia negative. In that way, we will still have a great classifier which has like 99%, almost 99% accuracy. But that doesn't make sense at all, because every time you just predict a patient that's healthy, and you didn't predict pneumonia at all. That's why we come up with this kind of ROC kind of way to measure the performance of the model. And the key idea there is that, let me go to this nice visualization. So the key idea is that we have this on the blue part is the negative cases, and the red part is the positive cases. Think the positive one as the patients who have pneumonia, and the negative ones as the patients who don't have pneumonia, right? So in this case, we probably have a great classifier like this, where we can easily separate those two conditions. So in this case, we have a great classifier like this, and no matter so the like this is like the visualization. So this vertical bar is like the confidence, kind of the threshold we talked about. So if we set the threshold here, then we are pretty sure that all the confidence that is lower than, let's say this is probably 0.4, then all the predicted number that is lower than 0.4, we can almost say for sure that the patient doesn't have any pneumonia at all, right? And if we have the number, and if we have the threshold as 0.8, and we are pretty sure that as long as the number is larger than 0.8, then the patient definitely have pneumonia, something like that. This is a great classifier, right? But let me change it to a different classifier like this, where we have trained this poor classifier, and we have this kind of overlapping area. So in this case, we still need to tweak the threshold, because in production you want to tweak the threshold a little bit, as Mason just talked. But in this case, let's say even we move it to here, like some number here, we are still not sure, like, for example, let's still put it here, like 0.7. For the number, for the confidence score that is larger than 0.7, well, you can't say for sure that whether the patient is healthy or not, because you still get a lot of those kind of blue areas here, right? So this is definitely a poor classifier. And if I move it further, like they are almost overlapping on each other. So in this case, the model will probably just be random guessing on something, like whether it has pneumonia or not. So in this case, for example, if I put the threshold here, then if the model, if the prediction is larger than, let's say, 0.6, then I can't tell anything here. So that's to answer the audience first question. So basically, that's the kind of the difference between a good model and a bad model. So for a bad model, you have this kind of overlapping areas, and for a good model, you have this kind of two areas very separate. And let's say we have this kind of decent model like this, and we still want to tweak this threshold a little bit more, because in production, like, for example, the clinicians will be notified when a certain disease is happening on a certain patient, right? So we also want to tweak this threshold a little bit more. There are different strategies here. For example, for positive cases, we can say that if it's larger than 0.7, then we have the final prediction. Or we can have another case where we have two thresholds, where we have a threshold for negative cases, and we have another threshold for positive cases, etc., etc. So there are different strategies here. But you definitely want to train a great classifier first, and then you want to go through the tuning for the threshold part. Okay, so basically that's the reason why we want to choose this RC curve, and that's why we want to tune the RC curve. And the final score we report is the AUC score, which stands for the area under this curve. So as you can see, if we have a great classifier, then the area under score is like 0.9 or nearly 1. So which means that we have a great classifier. Or if we have a poor classifier, then we will have a AORC score that is close to 0.5 or slightly larger than 0.5, which means that the model is just doing random guess. So that will be the number we finally report. And this is the RC curve that we get for this particular model for pneumonia, this disease. And as we discussed, we will want different AORC curve or AORC score for different diseases. So instead of looking at 14 diseases, we actually do the final testing here. And this is like our final result for the actual testing, for the actual test data set. So as you can see, we have good results for a few of the diseases. We are doing okay for most of the disease, and we are doing poor for like 1 or 2 of the diseases. Of course, there can be further improvements, like as we talked about, we can train an individual classifier for individual disease, or we can like put more data there, or we can probably do even more much more like data augmentation, etc., etc. So there's still, of course, a lot of room to improve. Okay. So I think this will almost be the end of the tutorial. So any questions here for all the models, etc., etc.? By the way, you will get like great scores like this. Like you have 1 for some of the disease. So don't believe in that. So because first, this model is really just a train on like a few, like 10 patients. So it's overfitting a lot. And also like for some of the data, the model already seen that. So that's why it can predict like 1 for some of the disease. So really don't trust that. Trust the table below. Trust this one. Okay. So yeah, to sum up a little bit, so basically through this quick tutorial, hopefully you learned how you can build your like first medical image classifier, and after that you also learn how you can evaluate the model, and after that you also learned a little bit on how to visualize the model, so you are more confident about the performance of the model. Okay, so after that, we will have like a 10-minute break. And after that, we will show you how you can use this model, export it to like some format, and you can run it on your phone or on your like laptop, etc., etc. Okay, let's have a break. Thanks.
Great. So hopefully everyone has a good break, 15-minute break and so. Cool, so let's get started. So my name is Wilson Lee. I'm a senior software engineer at Microsoft in the AI CTO office. Today I'm going to talk about 3 steps to build an intelligent application in healthcare. Now, before I continue, I want to ask a question. Show of hands, how many developers do we have here? Okay, we have several. Awesome. Now, what about, have anyone have experience building AI applications, even though you're not a developer, on your spare time or at work? Show of hands. Great, awesome. So this will be a fun session. Great, sounds good. All right, cool. So when we talk about building intelligent application, right, in my world, we're talking about 2 different types of things. We are thinking about, so for example, we're asking ourselves, where does my intelligence come from, right? So where does my intelligence serve? Is it on the cloud or on the edge, right? In the cloud, it means that maybe I use some pre-built AI, such as content services like OCR, translation, and so on and so forth, that is in production on the cloud, managed by one of our favorite cloud providers. And then I can call it as an API and actually bring it to my application and use it that way. So that's one way. Another way we can think about it is that we can actually bring a custom model, just like the one that you guys follow Xiaoyong and build, and we can actually put it on the cloud and in maybe an Azure Kubernetes services as a container, which you can serve as an API or using AML and so on and so forth. Also call it as an HTTP call, where you can actually bring the intelligence into your application. So that's one way. So that we call intelligent cloud. But then today I want to focus on the intelligent edge, which means that the intelligence itself, or the model itself, is actually evaluating on the device itself. Now, this is an architecture diagram that I really, really like. If you look at it, how we actually build this application, we are taking some of the data. So for example, some of the chest X-ray data that you've seen earlier, we actually build the model on maybe a deep learning virtual machine, so DLVM. And then we actually deploy it onto different intelligent apps or different intelligent device, right? So for example, Core ML, and you can deploy it on an iOS device like an iPad, or TensorFlow on an Android phone or Android tablet. Onyx, which we'll talk about a little bit more today, can deploy to a Windows 10 machine and running with Windows ML. Or you can even have a container, which is Docker image, that you can actually even deploy to an IoT edge device like a Miniport. And then you can actually run your model that way. So this is what we're talking about when we're talking about intelligent edge. Now, today we're going to take a look at deeper dive, and we're definitely going to look in code to take a look at the 3 steps that we can build an intelligent application using something called Windows ML Explorer. Okay. So what is Windows ML Explorer, or Windows Machine Learning Explorer? It's an application that we have built to showcase that we can actually run these models using Windows Machine Learning and Onyx. Okay? So before we deep dive into the code itself, let's take a look at some of the technologies that we'll use, right? So we mentioned something about Onyx. So how many people in here actually heard of Onyx? Great, several hands up. All right, awesome. So Onyx is a open neural network exchange, which is a framework that several big companies like Microsoft, AWS, and Facebook, and many other companies come together, want to actually build a standard, right? So then you can actually run these models. Now, this is a slide that I really like because it actually shows you exactly how a developer works with a data scientist. So myself, I'm a developer, Xiaoyong is a data scientist. We work together this way, right? As a data scientist, you care about, all right, I'm going to use my favorite framework like CNTK, TensorFlow, Caffe, PyTorch. When I say favorite, it might be because there's some limitation, libraries, etc., or something that you're familiar with, and you build a model that way. You train your model using those frameworks, right? Then you convert it into ONNX, right, which is a standard framework. And then you have a platform layer, just like Windows Machine Learning, that can actually execute this model for you, and then it can actually decide that if we want to use CPU or GPU, so it handles everything for you. For myself, a developer, all I care about is that, okay, so I get the model as an ONNX format, and I know, several lines, and we're going to talk a little bit more about that can call and actually evaluate this model, and then I can run it into my apps on IoT, on Windows, or on iOS, Android, where I can now focus on less about the AI piece, but more on the fact that I want my application to be efficient, it doesn't no memory leaks, it has great user experience, and etc. So this is a great way to look at how a developer like myself work with a data scientist like Xiaoyong. One of the great funny thing is that usually the way that Xiaoyong and I actually sits across the table, usually when the model doesn't work, I always say, hey, Xiaoyong, it doesn't work, and give me a new model. And then when he's trying the app and he finds bugs, I say, hey, there's a bug, and I go fix the bug. So that's how we work. Now let's talk a little bit more about Windows machine learning, right? So Windows machine learning is actually built into the Windows platform itself. It allows developers to integrate their trained machine learning model into their Windows applications. Now, the better way to look at it, it looks like this. So this is the stack. So you can see that you build applications. So you have either your C# application or your C++ application that actually call into the WinML-RT API, so the Windows SDK, right? While you actually load the model into your application, the Windows ML-RT layer will actually trigger the Windows ML runtime to load the ONNX model. And then underneath the service, which actually calls the direct ML layer, it will actually call and decide to actually use the CPU or GPU for inferencing. So basically something like that. Now, to understand a little bit more before we actually dive into the code, Windows ML development pattern, there's basically a very simple three-step patterns, right? You first load the machine learning model, right, into your app, load a model. Then secondly, you bind the inputs and output. What does that mean is basically you create the objects for the input and the output of the model. So what you're gonna feed into the model and what you'll get back as an object from the model. Then you evaluate. When you evaluate, then you actually get the result, and that's how you show in the app, and voila, that's how everything works. Now, we're going to use the Windows Machine Learning Explorer as an example. And in order for anyone to run this Windows ML Explorer, you need the latest Windows release, so RS4 release, so 1803. You need the latest Windows SDK, and also the latest Visual Studio IDE. Now, for everyone who is here who actually has these specs and would like to follow along, I would encourage you to actually go to GitHub and clone the repo. But we also understand that not everyone is using Windows and might not have all these things installed. So you can follow along, and then we actually dive into Go together and take a look. And when you go home and you want to actually, hey, give it a try or use this as your base project, you can actually do so and create your own intelligent application. Great. So let's take a look at the code. Okay. Right here. Great. Once you go to your GitHub, and maybe I can actually even show the GitHub right here. You should clone it from GitHub, just like any other project. So I can show you here, k.ms. This is WinML Explorer right here. All right, perfect. So you'll see it like that, and you'll find all the files in here. Now, once you clone the project, you'll see that the folder structure looks something like this. Sure, go to aka.ms, whack WinML Explorer. Okay, so that's a shortcut. It's right here. Oops, sorry about that, in here. And don't worry about it. We will also have a link at the end, and then you guys can actually copy that as well. All right, so in here. Now, after you actually clone the project, you see that the folder structure looks something like that. Now, before that I continue, now this is a live demo, hopefully everything works. So let me actually do F5 and actually run it to make sure that, hey, it actually works. So when you run the application, this is a very simple UWP application. So UWP is Universal Windows Platform that are, so all the Windows modern apps that you see on your Windows machine, those are UWP. And we use C# to actually write this code. And you see that we already have a model loaded into the application itself. Now the model that we have loaded, we call it circuit board defect detection. So basically what happens is that imagine a manufacturer actually producing circuit boards. Some of them maybe have some of the soldering, broken and things like that. They want to detect that, hey, if something is wrong and things like that. That's the model that we actually loaded as an example for this particular tutorial. So if you click on this button, you see that, hey, all the images. So for example, for these one, you see all these lines are broken and things like that. You say, hey, it's defective. Or you can actually use something that is maybe a little bit better. Some of the lines are cut off because of the size of the image, but you can see that this one has pretty complete, and we call it, hey, normal, non-defective, right? So as a showcase, you already have that model loaded. Okay, so let me close this. And let's take a look at that inside the code itself. Can you guys see the folder structure, or is this too small? No. Okay, so let me see if I can do this. Say it again? This is the solution, the base solution that when you go to the repo, you see the base solution and you will have that. And one thing to note is that you will need the latest Windows version. You need the Windows SDK, and you need the Visual Studio IDE to actually run this. All right. So hopefully I have the magnifying glass shown here, and hopefully that you guys can see a little bit better. So there's a couple of folders. So let's go through some of them so then we actually know. So the model that you guys seen before is the PCB. So it's printed circuit board in here. And you see that we have a folder with the images, which is, I'm sorry, I'm not very good at controlling the magnifying glass. So hopefully, I'll try my best here. All right. So you see that there's images, and you also see that there is an Onyx model, which is the model that we use, that are located in here. So those are actually in our asset folder, okay? After that, you'll also see that there are the standard controls in here. They're not actually standard controls, but they're controls that we built for the UWP app that talks about, hey, we have a control for the camera, for example, header, footer, and image control when we loaded the image. Then we have a folder called ML models, okay? So what this does is that we have the PCB models in there that is actually code that actually does the 3 steps that we talked about before, right? Loading the model, binding the inputs and outputs, and also evaluate. So we have that in there. We also created an abstraction called WinML model that actually, you can actually, that we have put in there that actually fits a little bit better with our app. So then you can actually change model through the dropdown, and we can show all that a little bit later on. Then inside the model folder, you have something called the, so this app is actually written on a MVVM pattern. So then you'll see that, hey, we have the property model that exists in here, and also we have a property model that are the results. You also have a folder for styles, so that's basically all the formatting of the app itself. You'll find something like that. And you also found some utilities that we deal with this device and storage and so on. And of course, at the end, you also see the view model that are here that you can see the pretty pictures, the pretty UI that we've seen shown on the app itself. So all of them are in there. Now, let me turn off magnifying glass. Okay, sounds good. So now, next step. So now we have some models running, which is great. Now let's bring in the model that you've seen a little earlier, the chest X-ray model that we have produced earlier, right? So how do we do that in this particular application itself? So basically what I've done is that in the asset folder, I've created a chessxnet folder in here. Sorry, in this one. Oops, sorry about that. Right here. I have the images. And also I have some labels. So you remember that when Xiaoyong talked about the diseases, so these are all the diseases that we actually are able to label inside the chessxnet model itself. So there are 14 of them, and each of them represented by an index. So that's one thing. Now, what we'll do is that, and also of course in the image file, we have all the chest X-ray files that we have in here. Okay, so the next step what we'll do is that we'll try to bring in the Onyx model. Okay, so I already have an existing item inside this folder itself. So in the asset, I have chestxnet, and let's bring in the Onyx model. Okay, in here. Cool. Okay, so in here you see that the Onyx model is actually created, or actually added to the project. Now, one thing that you might notice, and it might be a little too small, but let me see if I can show you this. So, one thing that you'll notice is actually a new file that is actually created. Now, this is a feature inside Visual Studio for Onyx models, where they actually automatically create a wrapper or a wrapper class for you to actually call into the model itself with those 3 steps that we talked about. So if you look at this, we have an object for input. So this is a video frame. In this case, a video frame in this context means an image. A frame in the video, which is an image represented by here. So this is the input object that we'll need. Now we also have the output object. So what happened is that you'll see that it actually have a list, a floating point list of the output. So yep, go ahead. Sorry, you mean the text bigger? Okay, so let me make it even bigger. Cool, better? Perfect, sounds good. All right, so you see that, as I mentioned before, the first class in here is the input, the input that you put in. In this case, it will be an image. You also have an output, which is here is called the chest X-ray model output. Okay, so this output, which actually comes out with a list of floating points. So this is basically the tensor that talk about for each of these diseases, what are the probability that it is, that particular disease. So that's one. And then we have the actual model class itself, which actually talked about in this line of code, line 31, it actually loads the model. So remember the 3-step? Load. So this is the particular line that actually say, hey, we'll load the model itself with the file that points to the model. Then once we have the model in here, we call evaluate, okay? So when we call evaluate, we initialize the output object in here in line 37, and then we do the binding and saying that, okay, so with this particular model that we have, so you see that in here, actually initialize the learning model, we bind the input and we bind the output over here, okay? And then the last step, very simple, is called evaluation. And then with the output, then you actually can show it to the app, okay? Does that make sense? Perfect. Sounds good. Now, this is one way of doing it, and with this particular file that is auto-generated by Visual Studio, you can actually call this file and you can run it. Or in our cases, because we want to be able for the application to actually switch models with the dropdown, and I can show you a little bit on that, we actually created a new model that is actually pretty similar to what we talk about, the 3 steps that we talk about, load, bind, and evaluate. And then we put it into somewhere in here. So let me show you this, and then we can, so it's outside of assets, we actually put it in ML models. Okay, so we call it chestxnet model. So all this does is that it actually adds a layer of abstraction, basically. All it does is that it's very similar to the file that you guys seen before. So you actually have the input object, you have the output object. You also have the model itself that actually extends the Windows ML model object that is basically an abstract class. So then we can actually control the display name. So we want to call it, for example, the chest X-ray. We want to, for example, saying, okay, if anything that's more than this probability, we're probably not showing it. We give it a name, we give it some pretty colors, and we tell it, hey, this is the Onyx model that you want to load, and also the labels in here in line 55. And basically, the rest of the code is very similar to what you've seen before, which you evaluate the model with an input and output. Okay, cool. So we are done in here. Now, last step. The last step that you need to do, for example, for this particular app, is that you need to go to main view model, which actually enables this object to be part of the dropdown. And now, with that saved, and now compile, hopefully no errors. I'm actually running live right now, so let's see. Okay, it's compiling. Compiling. hope I didn't make it. Oh, there you go. Okay, looks good. Now the app runs again. Cool. Oh, hold on. Ooh, I missed a step somewhere. Okay. Oh, I see why. Now, it actually threw an error. The reason why is this. So, one thing to note is that when you import an ONNX model, you actually have to change this manually for now. We are actually talking to the team to actually fix this as a bug, but then you have to set it as content. So what happened is that when you bring in a model, the project itself doesn't know what it is, so it's actually not included as part of the binaries. So when it compiles and run, it doesn't bring it to the as a package with the application itself. When you set it as the content, then now it will. So hopefully, I'll press F5 again, and hopefully that this time it will work. All right. Okay. Now the application runs, and voila. Okay. Now, what we have done here. Earlier, you see that the dropdown only have the circuit board defect detection. Now we actually include the lung disease prediction as well. So if you actually select on that, now you see that the name changes to lung disease prediction over here. And you see that, hey, select X-ray to start, for example. Then we can do similar things from the images that we ported into the application itself. So let's say if I select this one, now, and you'll see the result that, okay, so we believe that this is most likely is pleural effusion in this particular image, chest X-ray image itself. And all this is actually run locally on the Windows machine itself. So in theory, if I actually unplug the network cable, this will still run. Now, because of the fact that we can actually run this locally, we can actually even do this. We can actually turn on the camera. So let's see if this works. And then we can actually do this in real time. Hopefully this works, as you can see. And you see that I have a chest X-ray picture here. Then it actually works in real time. Now, it's a little slower because it's actually over network right now, but over network by meaning that this is actually running on a VM, and also sometimes the lighting and things like that changes a little bit, but this actually works on the first image. So, okay, so let's bring this back to this one, so you know that it works. All right, awesome. So it actually works. So this is how we create this using Windows ML Explorer. Any questions so far? Cool. That's good. Go ahead.
So there is instructions on that site to run this. So once you clone the GitHub, there are instructions to run this locally?
Yeah, and we can talk a little bit about that, about the resource and things like that, but we actually even have a blog post to actually walk you through. We even have videos and show you how to actually using some of these things as well. Perfect. Now,
so we can easily swap some other model with this model instead of the chest X-ray. If there's something else, we can easily swap into this code.
Yeah.
Make that to detect that. Say if it is for some other detection.
Yeah, if it's an ONNX model and with an image classification model, it should be similar to how we actually do it on the particular app itself. So it should be very similar things. So just like how we did it in here, to add the chest X-ray model into this, and it actually should be very simple. Perfect. Now, next thing I want to show is that, okay, so we've shown it on Windows ML. Okay. Let's show it a little bit more. Do you remember that? So what happened is that our intern team at Microsoft Vancouver Garage interns, they actually built a mobile app that using the similar model that you guys have seen, the chest X-ray model, and put it onto a using TensorFlow to run it in Android, and also using CoreML running on iOS. And actually, I have the demo app here to show you guys. All right, so it's right here. Okay, so hopefully you guys can see.
One more question.
Yep, go ahead.
On this application, it
Yes.
talks about Windows ML. Is that going to be on my local computer? I can install that Windows ML? Or?
Yes, so Windows ML comes by default with build 1803 and more, so RS4 and more. In order for you to run it, you need that build and of course any later build.
Windows 10 version.
Yes, you also need the Windows 10 SDK and the latest Visual Studio IDE. Perfect.
So that's for the building part, but in order to just run the application, you don't need that. Like it's just like a regular UWP app.
No, you do. You still need it. You do need it. You do need the You don't need the SDK, but you do need the latest Windows version.
Oh,
Yes.
Yeah, the latest
There you
because it has a Windows
Yeah.
ML.
Yes.
Exactly.
Okay.
That's it. Any other questions on Windows ML Explorer? Go ahead. Yes, not for that particular application because it's actually a UWP application. So that the application won't run anywhere else other than on Windows devices. Yeah. Yeah, so basically, when you say transfer apps, so you're thinking about like Android and iOS and things like that, right? So within that, you can actually take that model and actually build, and this is a great example of that. So basically what our Garage intern have done is that they actually took the model, exact model that you guys seen before. They actually built a Xamarin app that actually can run on both Android and iOS, okay? With that, on this one is an iPad, so you can see the application looks like that. We call that Mobile Chest X-Ray, okay? And basically, you see the similar functionality. You can actually grab the photo from the iPad itself, and voila. And then you see, and actually do the inferencing locally. One additional thing that they have done is that they even able to actually put the, let's see if you guys can see the blue, the area that is actually infected and things like that. So this application and so on and so forth. You can actually also do it live. Maybe, let's see if I can actually take a picture of this application, take a photo. Okay, so let's see if this works. Here, this is a little bit tilted. Sorry about that. All right, let's do that, see if that works. Okay, so we have that, use photo. Okay, so you can even adjust. So for example, let's say, okay, my picture is a little tilted or a little bit not correct, then I can actually adjust this and actually run it. And now you can actually see the actual result in here as well with the their area that's infected also highlighted in here as well. Now, you guys can actually, all this is actually available. Let me go back to my slides. And all this is actually available on GitHub. You'll see the link for the Windows ML Explorer on the first aka.ms link. For the Mobile Chest X-Ray, they also, the code is actually on GitHub itself. You can go to GitHub, Microsoft Mobile Chest X-Ray Analysis. And also the all the tutorials and the training, the steps to train the model itself that Xiaoyong showed a little early on the first part of the tutorial. You can also find it on github.com, Azure Chest X-Ray as well. Awesome. So this concludes my app. Hopefully that you guys can give you enough information to start to create your own intelligent application on either Windows ML or on Core ML or on Android devices. Sounds good. Any questions? No? Great. Sounds good. Thank you.